Good morning, everybody. Thank you for being there despite the fact that it's early in the morning. Okay, so yesterday we stopped while discussing the band spectrum in a sinusoidal periodic potential. We saw that if we have no amplitude of the lattice, of course, we're back to the case where we have free particles and we have a parabolic spectrum that we can interpret in terms of band by folding the spectrum each time it goes beyond plus or minus k. And so each time you fold it, you get a new band, of course. Now, if the lattice potential is not 0, but it's still small as compared to the typical energy scale of the problem, so the energy to the next band, which is the recoil energy, then we can make a perturbative approach around the region where there was a crossing at the edges of the first Brillouin zone. And because of the coupling now, this crossing is an avoided crossing, and a gap opens, and the size of this gap is half of the lattice depth, V0. So now let's consider the opposite case, which is also easy to discuss analytically, which is the case where the potential is very deep, and so the lattice depth is much larger than the recoil. So in this case, you will have very deep lattices. And if you want to know what is the fundamental band or the first excited bands, they will be localized at the bottom of the lattice, and each well will behave independently from the neighboring well if the lattice is very deep. So at some point, the barrier between two wells will be so high that the wells will just behave as independent, locally harmonic potentials. So if we look around one particular well, so say the one which is at around 0, and I use again the same potential, sinusoidal potential in sine kx squared. Around the position 0, I can expand the potential as V0 k squared x squared, which I can write under the form 1/2 of m omega squared x squared, where so I call it omega naught just to be consistent with my note, where omega naught is some harmonic frequency. So what I am doing right now is to say that if the lattice is deep enough, the atomic motion will be localized much more than the wavelength. So the atoms will not explore beyond their own well. And so if this is true, it means that kx will remain very small as compared to 1. And so the wave function will be localized much better than 1/k. And I can make a harmonic approximation close to the bottom of a given lattice well. It means that I make this kind of harmonic approximation at the bottom of the well. And the harmonic frequency which comes from this expansion is related to the lattice depth and to k. So if I identify here, I find that omega 0 squared is 2 V0, and then I have a k squared over m. So let me write it in terms of energies. And I will write that 2 is nothing but 4 divided by 2. I hope you agree. And what I can see is that this guy here, I know, this is a recoil energy. So the harmonic oscillation frequency at the bottom of this independent well scales like square root of the lattice depth times the recoil frequency. So if I measure all the energies in terms of the recoil, if you prefer, it's twice the square root of V0 in units of recoil. So the oscillation frequency is the recoil frequency times twice square root of V0. So as I made the assumption that V0 is very large as compared to the recoil energy, I have to conclude that the oscillation frequency is very large as compared to the recoil frequency. So this regime is very interesting in metrology. It is called the Lambda regime. For which the level splitting of the harmonic oscillator h bar omega naught is much larger than the recoil energy, which is a typical energy change when there is a scattering process, absorption or emission of a single photon. And so why is it interesting for metrology? Well, this is at the basis of the new optical lattice clocks. And the idea is that if now you have an excited state which is trapped, so let me concentrate on just one well. And let me assume that the atom has an excited state which is trapped exactly in the same way. I will discuss this later, why it is possible. So I have an excited state with exactly the same level spacing that in the ground state. And so there are possible transitions between those states. And this comes back to the lecture of Philippe, where he showed that there was an amplification of the probe or a absorption of the probe depending on its frequency with respect to the pump, and there was a peak at the oscillation frequency inside the well. So here it is the same story. What are the possible transitions? So you have the transition at, I would call it the carrier. So this is a usual atomic frequency. The frequency difference between the ground state and the excited state of the atom in the absence of any trapping. So in metrology, that's the thing you want to measure. And then, so this happens when you make a transition between one of the oscillation levels and the other one, the harmonic level and the other one, and the same one in the other well. So n is 0, 1, 2, 0, 1, 2. So this transition occurs between the excitation n in the ground state and the excitation n in the excited state. You can also have a transition between a level n and a level n plus 1. And this occurs at the frequency, which is the atomic frequency plus omega naught. Or you can have a transition between the level n and the level n minus 1 And this occurs at the frequency, atomic frequency minus omega naught. And what's happening if you are in the lambdical regime, that okay, this kind of transition you can always reach by having a laser intense enough. But why do you need an intense laser to couple? So what is called the blue sideband, because it's at a frequency larger than the atomic frequency, or the red sideband, which has a frequency lower than the atomic frequency. This is because the dipolar element, so the dipole element is e to the I kx. Okay, I am 1D. So this is a dipole element. And you want to couple a given state n with another state n prime, say. And n and n primes are eigenstates inside the harmonic potential. So what you will use is that the x operator, kx, will always be very small with your states here, because the trap is pretty much confined. So the extension of this state here, if I look at the x squared, that's about n. So the size of a state, n times the ground state of the harmonic oscillator, and the ground state of the harmonic oscillator is h bar over m omega 0. Okay, so as this is very large as compared to the recoil, this thing is very small as compared to k minus 1 by assumption initially. So this x here is, this kx is very small as compared to 1. So you can make an expansion and say that this is approximately 1 plus a perturbation. So 1 will give you the scalar product of n and n prime, and then perturbation, which is x, k, and then the x operator between n and n prime. So this is what is very small, because this is on the order of square root of n, well, yes, square root of n a0. And this is 0 unless n is equal to n prime. So it is delta n n prime, and then something small on the order of k a0 and something small. So when you are in the lambdical regime, it means that coupling two levels of the harmonic oscillator by a photon in an absorption or spontaneous scattering process is very difficult unless n is equal to n prime, because this will give you a first order, or if you look at probabilities, can be second order terms, in terms of the lambdical parameter, which is this k a0. In other words, if you have strong power, you can beat this problem by still exciting a transition at n to n plus 1 or n to n minus 1, but spontaneous emission will be negligible outside the main carrier going from n to n. So this is something which is used in strongly confined atoms or ions to cool down a sample by shining a laser on the n to n minus 1 transition. So if you do so, each time you go in the excited state, you lose one excitation in the trap. And spontaneous emission only occurs with the same n. So in a cycle, you go from n to n minus 1 when going from G to E, and then back to n minus 1 when a spontaneous photon is emitted. So each cycle removes one excitation in the lattice or in the trap, and at the end of the day, the atoms accumulate in the ground state, which is not coupled by the red sideband because there is no n equals to minus 1 in the excited state. So this is a way to prepare atom in the ground state of a strong confining trap. And for metrology purposes, the idea is to have this energy, so very large as compared to the recoil. And in this case, you can very nicely send the all the Doppler broadening away from the main carrier, and you get a spectrum, an absorption spectrum for your for a probe interrogating this type of atom, which is like that. You have the atomic frequency at the center, atomic frequency plus omega 0, atomic frequency minus omega 0. So a very narrow carrier in the center, which is the clock transition, and then a red sideband and a blue sideband on the sides, where all the Doppler broadening is rejected, such that you are able to properly interrogate just the clock transition. So why is this one higher than this one? Because the atoms are cold, and so most of the population is in the ground state, such that the red sideband is almost forbidden, whereas the blue sideband is always possible, even if the atoms are in the ground state. So this is similar to what Philippe described. And how now is it possible to have exactly this situation realized with atoms for the clock? So the trick is, so for ions it is easy in a sense because the potential is done with the electromagnetic interaction of the charge with some electric trap. And so the internal level of the other electrons which are excited in the transition are not involved in the trapping. So the trap is more or less independent. The trap catches the charge of the ion, or it is the same in the excited state and in the ground state. But for atoms in general, if you remember the lectures by Philippe, I don't know if he discussed that, but if you try, for example, to have a dipole trap, the potential you will have in the ground state is something, but in the dressed atom picture, the potential in the excited state is just the opposite. So it's not the situation I have drawn where I want to have the same potential in the excited state and in the ground state. So the reason why it is possible and it is interesting for clocks is that, of course, there are not only two level atoms in the life. There are also atoms with much more levels than two. And in particular, to build a clock, you will use a narrow line, a narrow transition, which will be your interrogation transition. And all relies on the fact that if you, as you have many, many levels, you look for what is called a magic frequency or magic wavelength, for which so there are levels everywhere, and you use a frequency which is such that it will always push the ground state downwards, For example, because it is a red detune with respect to the G to E transition, not necessarily this one, but imagine this is this one. But you want that the E level is displaced exactly as the G is. So if you just have this transition, it will not work, because this one will push downwards and this one upwards. But now you have another one. And if the frequency of the photon is such that this one now is red for this level E, even if it's if it will push this level E upwards, it will be less than pushing the level E downwards because of this coupling here. And because of that, this will overcompensate the positive shift on E. And at the end of the day, you will have exactly the same shift for E and G. And this is what you are looking for. And once you are able to do that in a lattice which is sufficiently far detuned from both E and G to have almost no photon scattering, then you realize this configuration, and that's how you build optical clocks. Okay, so the thing I forgot to mention, of course, is that as we have a situation which is very close to just a harmonic potential, the bands, because I was discussing bands and block functions, so the bands are flat, essentially. If I draw the bands in the first Brillouin zone, so the first band is there, second band is there, third band is there, with energy h bar omega 0 divided by 2, 3/2 of h bar omega 0, etc. So this is what's happening in the limit of very deep lattices. So you recover the energies of the harmonic oscillator, and the bands now do not depend on Q anymore. Okay, so now I would like to show you numerical results in the various regimes I've just discussed yesterday and today. Okay, so the general lecture, the way to read the slides is as follows. So on the left part of the slide, I will compare the spectrum obtained by diagonalization of the Hamiltonian, numerical diagonalization, to the spectrum of a free particle folded on the sides. So here I take 0 depth, so of course they are exactly the same. The dashed lines are the one of the free particle and will always stay there, where the red lines are the one which will change when I will increase V0. And on the right part of the slide, when it is relevant, for the moment it is not, I will compare the band structure with the harmonic potential, which is relevant for deep lattices. So for 0 potential, they agree with of course, with the free particle. So for the moment, it's an exception. It's just a zoom. And now I take a depth of the lattice, which is just the recoil. So if it is just the recoil, what's happening is that if I zoom on the side of on the edge of the Brillouin zone, I see that indeed these two states which were degenerate at the edge now are not. There is a gap opening, and the size of this gap, so my unit here is always recoil. So one recoil is this, from there to there, and this is half a recoil, and as V0 is just a recoil, it agrees with the splitting of V0 divided by 2 that we get at the edge when the two free particle energies cross. So another comment, so this line here represents the lattice depth. So in case you have particles at very low energy, so they will be at the bottom of the band, which is less than the lattice depth. But you see that already the second well, the first excited band is entirely outside the lattice depth. So here, in a sense, the atoms, they are free because they have an energy which is higher than the lattice. So only around K there is a small deviation from the free particle spectrum, but that's essentially the free particle spectrum. So now let me increase further the lattice depth. So it means that the gap opening here will be larger. Okay? But now the potential is in between the gaps, so it's still a very shallow lattice. Now it's 4 times the recoil, and I start to have also the second band inside the lattice depth. And here I start to show you the harmonic potential level. So you see here that we have now the fundamental band which becomes flatter. So it's flatter than it was before. So it's neither really a free particle at the bottom nor completely frozen in the ground state, but it starts to be frozen. And when I increase V0 further, so you see clearly here that now the fundamental band is almost flat. So I'm close to the situation where in the fundamental band the atoms are in a given well. Still hopping is a little bit a lot there, but less. And the second band is deviating notably from the free particle, even if it's not yet flat. Okay, and if I increase further, now the second band becomes flat, etc., etc. And now, with very deep potentials, it resembles a harmonic oscillator in the bottom. Okay, I think, yes, I wanted to also show you what are the block functions like. So this is a plot of the modulus of the block function. So you can't see the phase yet here, I'm sorry. So I have chosen to plot the modulus of the block function in the fundamental band. And this one is for the central point at q equals to 0 for different lattice depths. So of course, for 0 lattice depth, it is flat because the solution is just a plane wave. And so the modulus of a plane wave does not depend on position, it's just always 1, so it's just flat. And once you add a lattice, you see that the wave function is modulated with a higher probability where there is a well, so at 0, minus a period, plus a period. And the more you increase the lattice depth, the more localized the wave function is inside the well. And when we go to the situation where the potential is 32 recoil, so we are very close to the situation where I said we have almost a harmonic oscillator at the bottom. And indeed what you see is that if I look at this curve, it almost goes to 0 in between 2 wells, such that it is pretty much localized inside a given well and then next and next. So the wells behave almost independent from each other. So this is for n equals 0, q equals 1. Now let me go to, again, q equals 0, but in the first excited band. And the parity of the wave function is reversed in this case. And again, you see that it is more and more pronounced when we have a deeper potential. And when we have the deepest potential, it resembles the first state of the harmonic oscillator. Okay, I think that's it for the moment. Yes. Okay, so the aim of this first lecture, which is now over, is to describe what are the eigenstates in a periodic potential, the Bloch theorem, and the fact that there are two limits, essentially, when the one where you have modified plane waves and the one where you have localized independent states. And in between, there will be a rich behavior where you have both localized state, but which can still hop from one well to another one. So this kind of description we will leave for this afternoon. But before that, we will study in a second part a bit of dynamics in the lattice or after switching the lattice, or from the lattice, in or from the lattice. And the first important point we will look at is the time of flight analysis. Which is a very important way to get information from the states of the atoms in the lattice. So the time of flight analysis is the same thing that Philippe described. So you switch off everything and you look at the position distribution after a long time. So what is long? If you have an initial size of the cloud, which is some delta r, you wait long enough such that the final position after a time of flight, which for each atom is given by its initial position plus its initial velocity times the time of flight, such that the delta r after time of flight is very, very large as compared to the initial delta r. Such that the contribution of this initial position of the atom within delta r is negligible with respect to the contribution of the momentum width brought by this term here. So the size after time of flight is approximately the time of flight times the size in V, which is the size in P, divided by M. So the idea is to be able to measure, in fact, the position, the momentum distribution, which is directly related to the position distribution after time of flight. So the momentum distribution, or the initial wave function in the momentum space, or I should not use k because k is maybe k laser, so let me use p, will be equal to the function you observed after cutoff at position p cutoff over n. So this is a way, finally, to just get the momentum distribution. So what do you expect? What do we expect if we start from a block function? now it's not on my slides, so you have to tell me. The answer is not written. So what do I expect? Yes?
Depends on the depth, but you will see several peaks.
And why should I see several peaks?
Because there is a spatial modulation. So you have a wave traveling in one direction and a wave traveling in the other direction. And they form a standing wave.
Yes, this is the beginning of the story. So why should I observe peaks? So I want to, I say I start from a block function, which is the eigenstate in the situation where I have a standing wave. So I agree I have a standing wave. I also agree with the last statement which says I should observe peaks, but I didn't quite get the reason why until now. Somebody has an idea? Yes?
The momenta, since you switch off the lattice property, are come back to like real space momenta. So from the quantum number, the magnitude is real space momenta, and then
Yes. So the point is that I will observe the momentum distribution. That's what I have written there. I will observe the momentum distribution. So the question is, what is the momentum distribution in my block state? And so the momentum distribution in the block state I wrote yesterday, right? Because I wrote the block function onto in the momentum space. And if you remember, it was a com of momenta. This is what the block function is. If I look in position space, I find these oscillations, etc. And if I look in momentum space, I just have a superposition of momenta with a very well-defined momentum spaced by 2h bar k. This is what the block function is, the way we've written it yesterday. And so this is exactly what I should get. So the block function written in terms of momenta. Let me write it like that. It's just a sum. So I call that alpha or j something, if I remember correctly. Alpha, q, and j, sure. Or like that. I don't remember, but n, yes. And there, just the p corresponding to that is h bar q plus j times 2 h bar k in the direction. So I did it for 1D, in fact, but this is true for or any direction. So some k. Let me write it h bar q, where q belongs to the reciprocal Bravais lattice. So it's a sum over the q's, and so it's an index q here, because I did it in 1D. So this is a formula for 3D. Q is in B prime. So this is what the wave function is in terms of momenta. And so what I expect is that after the time of flight, I will just have exactly that, except now all the momentum states are transformed into localized position states at the position h bar q plus q over m times the time of flight. So I expect to see peaks at positions in space which are regularly spaced by h bar q over m time of flight. So this is indeed what I should have left the thing on. This is a pity. I show you later because I'm lazy. Like, I will go to the next paragraph and then I show you all the pictures together. Otherwise, it takes too much time. Okay. So what you expect is to see in time of flight so if you start from a BEC, start from a very cold cloud, what's happening in this case is that you almost have only the Q equals to 0 momentum, quasi-momentum state, which is populated. So almost 0 temperature, no interactions. And so this is essentially 0 here. So you measure, in a sense, the reciprocal Bravais lattice. And you have, if you start from a square lattice, you will observe peaks, which are regularly spaced. And then a bit less here, because it's second order, and etc., etc. And this is what you expect to see. Now, in principle, if you have, then this is weighted by the coefficients alpha, and there will be an overall width of the diffraction picture. So this is a diffraction pattern, and the overall width is also linked to the frequency at the bottom of the well, because the larger the oscillation frequency at the bottom of the well, the larger the delta P in each of the wells. So this will give you the overall shape of the peaks. Okay, so this I will show you right after because I don't want to use the projector now. And I will go to another way. Yes?
I don't really understand. The first one, what do you mean by the initial state equal to some?
What do we mean by what?
By the initial state
Yes.
equal to the final state? Or so what's the right-hand side of the first one? It seems like the right-hand side is the argument of position.
Yeah, okay, okay. Within maybe, no, yes, that's it. Maybe within some prefactor or anything you like to transform a function in space in function in momentum. Some h bar, if you like. I can put an h bar, but apart some normalization factor, which I don't care because I want to measure a...
The idea is that you map the momentum distribution into a position distribution.
So this is in fact what Philippe explained yesterday, so I didn't want to do it again, but if you have an initial position distribution with also a momentum distribution independent from the position distribution, what will happen is that each single atom will have this kind of trajectory. So this one, for example, had a velocity like that. So after a long time, it will be there. And this one had a velocity like that. So after a long time, it will be there. And this one had a very small velocity like that. So after a long time, it will be there. And this one had a large velocity like that. So after a long time, it will be there. If the time is long enough, the fact that initially I had this little spot here with not all the atoms at the same position is negligible with respect to the final size of my big bubble. If I imagine that all the atoms start from the same position, I remove that, then the width in position after a time θ is given by θ times the width in velocity. And even the distribution in position is given by the distribution in velocity times the time. You agree with that? So the only thing is that there is a little discrepancy at the beginning because they do not all start from exactly the same point. But this is negligible as soon as this time here is so large that this little tiny difference here, this little uncertainty on the end of this arrow, is very small as compared to this big size here.
So you mean the final position looks like initial one?
Exactly, the final after time. So if you prefer, I write it, this is a position, okay? R equals to this, comma, T equals to theta is equal to the transform. Now I am in P momenta, okay? P momentum and at 0 time. This is what I wanted to write. Maybe I was a bit too allusive and fast. This is what I had in mind. Okay? Thank you for the question. Other questions? Okay. So let me now describe what's happening if instead of switching off the lattice abruptly, we switch it off slowly, adiabatically. So what does that mean? It means that we will make the potential depth vary with time, but slowly. So we will write the Hamiltonian as our periodic potential, but with a time-dependent function, dimensionless time-dependent function. And f of t is a function which starts at 1 and then goes down to 0 in some time, long enough. Okay, so first remark, so this is a time-dependent Hamiltonian now, right? First remark, V of R is always the same V of R. It has the same periodicity always. So whatever the time I look at, this H of T commutes again with all the translation operators with a lattice period. So at any time, H of T commutes with the translations of a vector belonging to the Bravais lattice. Okay, so let's consider an initial block state. So at 0 time, let me consider I work in the fundamental band because I don't want to have this n all the way there, or at some band. So I may forget to write n every time. So if there is no n, just put it again. That's not very okay. Initial means that at 0 time, f is 1, so we are in the starting lattice as usual. So psi nq at 0 time is an eigenstate of all the t, a, j with the eigenvalue e to the, so is it plus or minus? E to the I q aj, as we said yesterday. So now, is it still true at later time? So the wave function at later time a state at later time, at time t, is given by applying the evolution operator u to psi at time 0. But the evolution operator is built on h, which commutes with all the t. So also u commutes with all the t a I aj's. So if it commutes, let's see if the wave function after the evolution time t is still an eigenstate of t aj with the same eigenvalue. So does it have the same quasi-momentum? Let's check that. So if I apply t aj to now the psi nq after time t, so this is nothing but u of t psi nq at time 0, but u commutes with t, so it's u of t t a j applied on nq at time 0, which is an eigenstate of Taj with the eigenvalue e to the iqaj. So this is e to the iqaj u of t and just psi nq of r t equals to 0. But this is nothing but psi at time t. So we conclude that the psi at time t, which is the evolution of the initial block state when we ramp the lattice, is still an eigenstate of the translation operator with the same eigenvalue. So it has kept the trace of the track of the same quasi-momentum. Okay, so it is still a proper eigenstate of t with the same quasi-momentum. And the other argument I would like to make is that if f of t varies slowly, in addition, the weight over the various bands of the initial state, which can be a superposition of several block states, is conserved, is preserved. So if we start in a given band, we will stay in this band. This is what I'm saying. So the n, in other words, this guy here will be a block state of the new potential with the amplitude f of t. So this is true only if if f varies slowly. So in fact, we need to fulfill the adiabatic theorem. So if the way psi varies with t, for a given value, so now it's a kind of psi t where it is this eigenstate, block eigenstate of f of t v of r. So if this varies slow enough such that it does not project too much onto another band, so another block state with another band index. So we know that Q is conserved, so I put the same Q. But there could be, when I change F, that the block function in a given band couples to other bands. And if this is small enough, so small enough as compared to the energy difference between the band n and the band n prime, so if this is fulfilled, then we can state that indeed each block function, well, if we start in a block function with n and q at initial value v of r, when we will ramp the amplitude of the potential with the function f of t, we will always keep the same n and keep the same q and follow adiabatically the block state corresponding to this very n and this very q. And this is true if the evolution, the time evolution, imagine the bands, the n of q with time, they evolve. The gap will close essentially if I remove, if I switch off the lattice, the gap may close. And so this gap has to be large enough such that when I switch off the lattice, the projection of psi nq to psi prime nq, when I vary psi, is always very small. So I don't have enough coupling to change the band. Okay, so let's take the example where we start with q equals to 0, and we ramp the wave function linearly. So in this case, there is a constant rate f dot at which the lattice is run down. And then we can show that this rate has to be not too fast. If it is too fast, the wave function will change too fast and it will exceed this gap. So it has to be very small as compared to something like the square of the recoil divided by the potential, the initial potential wave. So there is a prefactor which in fact is larger, like about 50, something like that. So it's less stringent than that. But what it tells you is that if you start from a very deep lattice, you have to go slowly. Because if the lattice is very deep, then this thing will be smaller, so you will have to go slow enough. and essentially you will have to go like 1 over the lattice depth. So if you do so, you preserve the, in particular, you preserve the momentum, you transform adiabatically the final momentum into the quasi-momentum. And the reason why you do that is that imagine you you start somewhere okay, so this is more or less what the band structure is like. I take an initial block state with some Q here. And what I say is that Q is preserved. And the band is preserved. So what's happening when I switch off the lattice is that I know that I will go to the parabolic dispersion relation. So the parabolic dispersion relation at the end I can draw at the one which goes there and here. Ouais, attends, non, elle est de l'autre côté. Oui. Attends. Elle passe au-dessus de celle-là, donc elle se croise. Oh, c'est bon. Oups. Bon, je dessine très mal, hein. C'est connu depuis la nuit des temps. Okay. So anyway, if we start in the fundamental band with the quasi-momentum Q, we will end with a free particle which momentum, real momentum now, will be just h bar q. So we will transform the quasi-momentum into real momentum. This is if we are in the fundamental band. Now, if we are in the first excited band here, imagine we start from there. So this one maps onto this momentum, which is the same, this one, as the one where I can translate by 2h bar k. So this branch here, I recover here, of course. So this state here is exactly the same as the state where we have q plus 2k. And when I think in terms of real momentum, this is the parabolic curve I end with. So here, I end in P equals to h bar q plus 2h bar k for the first excited band as soon as my q is negative. If the q is positive, then I will have h bar q minus 2h bar k in the first excited band. If I was in the second excited band, then I will have h bar q plus 2h bar k for k positive and h bar q minus 2h bar k for k negative, because now I'm close to 4h bar k, etc., etc. So it's also a way to determine how many atoms you have in each band, because all the atoms which have a momentum between minus q and plus q are the ones which belong to the fundamental band. And if I see some atoms here which are between k and 2k, all these ones here up to this point, they belong to the first excited band. All these ones I will find here belong to the first excited band. So I should put them in yellow. So all these ones belong to the first excited band. Whereas all these ones here, they belong to the fundamental band. And if I found atoms at momenta exceeding plus or minus 2 h bar k, which are between minus 3 h bar k and minus 2 h bar k, or between 2 h bar k and 3 h bar k, they belong to the second excited band, etc. So then I can just count the population in each of the bands using this method. So now I would like to show you two pictures from experimental data illustrating both the rapid switching and the adiabatic switching. Okay, so this is a very nice picture of a diffraction pattern we obtain by switching off abruptly a lattice where the atoms occupy the ground state with Q almost 0. And the lattice is not very deep, so you have a very nice block state. And in this graph, interactions play a limited role. So it's almost just a block function. And as expected, when you look at the position distribution at long times, it reflects the momentum distribution in the lattice initially. And you find a very strong peak at momentum 0, and also peaks at momentum plus 2 h bar k, minus 2 h bar k, etc. So the initial lattice is a square lattice with period lambda over 2 in all 3 directions. So in 3 dimensions, you can reconstruct the full momentum distribution, which is the Bravais lattice of the reciprocal lattice. So you can see that at short times, it's hard to see anything because there the initial size is not negligible. So you cannot really make the assumption that what you observe is a momentum distribution. Okay, the initial size is too important. There also, and the more you wait, and the more nicer you can identify the peaks in direct space with the momentum distribution before releasing the cloud. Okay, so this is taken from Markus Greiner's PhD thesis. And another way of switching off the lattice is the Adiabatic Opening. So here is an example of the drawing I've shown just before, which is behind the screen now, where imagine you start in the fundamental band and a little bit in the first excited band. Once you switch off, well, this is just the same picture as this one, but instead of concentrating only on the first Brillouin zone, I can also decide to use other values of Q within a period 2K. So here the fundamental band is still represented in the first Brillouin zone, but the first excited band is represented with shifting by plus 2K this left part and minus 2K this right part. And then the second band is represented such that this left band is shifted by minus 2K and this one by plus 2K. And now it becomes very clear what's happening when you lower the lattice adiabatically. You are supposed to preserve both the band index and momentum, quasi-momentum. So just what will happen that these gaps will close and you map onto this, which is just now the dispersion of a free particle. And here is the momentum distribution you will observe. So if you had only population in the fundamental band, you would observe only this part here. And the fact that there are atoms here means that there was some occupation in the first excited band. So this is an example where just the fundamental band is populated, but is populated everywhere. So this you do, for example, by exciting a little bit the cloud in such a way that you populate all the first band by giving some energy, but not high enough such that you populate the first excited band. So you give some energy, but still less than V0. Yes?
One short question. The edge is rather smooth in this picture. Is this because part of the cloud is not in an adiabatic condition, and that's why we see kind of that it smooths out of the second band? Or
Yes. Yeah. In fact, the point is here you cannot be adiabatic up to the end, because at some point the gap closes. And when the gap closes, by definition, you can never be adiabatic. So at the very end, you will always have some blurring with a little bit of the fundamental band going into the excited band.
could we use this, how smooth it is, to kind of measure in a way the temperature of the cloud or something? Would it be a non-rigorous way?
No, I'm not sure, because anyway, even if temperature is 0, you cannot follow the adiabatic condition, so you will bring some excitation in the other band just by varying the V0. So yes.
I think there's something I don't understand. If, for example, I start with forget about the lattice, I just have that resolution from the tip, and I let it fall. What I should see is just a big blob that is given by the
Yes.
distribution.
Yes.
So if now I have a lattice, and then I switch to adiabatic again,
Yes.
I should go back to the Bose-Einstein.
Yes.
But then, and if I let it fall, I shouldn't see this. I shouldn't.
That's why I said it was not a Bose-Einstein condensate anymore, and it has been excited. So they intentionally populated the whole fundamental band. If you start from a condensate and you do not jiggle it in some sense, it will occupy essentially Q equals to 0. And when you map back to a free particle, you will see a nice peak as in a Bose-Einstein condensate. You will see just the central part of the B1 zone occupied,
Okay, so
and it will be much smaller than plus minus K. So H bar K is a large momentum for a BEC. Normally, the momentum is much smaller. So if you have energies reaching the recoil energy, that's because you gave energy to the sample net. So what you do is that you start from a situation where you gave some energy to the sample on the order of the recoil to populate the fundamental band everywhere, but less than the gap V0 to the first excited band. So you give some energy which is on the order of E-rec, but less than V0. So it's a situation where, of course, V0 is larger than E-rec. Otherwise, and anywhere the bands, they are not well defined. So you start from a situation where you have a potential lattice deep enough such that you can isolate nicely the fundamental band and the first excited band. And you heat the sample in order to populate the full fundamental band up to the edges. And now you make the time of flight with the adiabatic releasing, and that's what you observe. But you have to look for this situation. Okay? And here is the situation where you heat so much that you populate also excited bands, and you can nicely observe the first Billouin zone, and then the second Billouin zone, which corresponds to the first excited band, and then the third one here, which corresponds to the second excited band, etc., etc., and count how many atoms you had initially in the different bands. So there was another question? No? Okay, so this is for bosons in a 2D lattice, and this is a situation where there are fermions in a 3D lattice, where you can see the same thing, except that for fermions, because of Pauli principle, already at very low temperature, you get a big blob because of occupying all the states with each with one particle. So when you add more atoms, it already fills, even at T equals to 0, there you don't need to excite. You just put more atoms, it will fill more and more the first Billouin zone, up to the point where if you have too many particles, this band is already completely filled, and you have to populate the excited bands to put more fermions. Okay, so I think, yeah, this is different. So I will switch. Il me reste un quart d'heure là, c'est ça? Wow. Ok. Bon. Eh ben. Okay, I will not describe effective mass and evolution of a wave packet in the band, for example, in the fundamental band, because I don't have time and it's in the notes. It's not something I really wanted to point here. Just to let you know the fact that you have the fundamental band, which is flattened because of the gap opening on the side. If you want to make a parabolic approximation of what is this band like towards close to q equals to 0, you can do this. And if you do it, instead of having like the blue curve curvature, which will be 1 over 2m, will give you p squared over 2m, you have a curvature which will be 1 over 2m star with an effective mass which will be higher, because the curvature will be lower as soon as you have atoms inside the lattice. You have a band which is flatter and flatter the deeper the lattice is. And you can describe this as giving an effective mass larger than the true mass of the atom to the atom. This is just the point I will skip in order to go to block oscillations. I will send the lecture notes to Mathilde right after the lecture, so you will have it very soon. Have them. Okay, so I directly arrived to block oscillations. So I don't know if I will be able to do it in 10 minutes. Seems difficult. So I will start, and probably we'll continue after lunch. So block oscillations occur when we add a constant force to the periodic potential. So we will stay in one dimension. It will be simpler. The Hamiltonian we would like to consider is essentially our p squared over 2m plus v of x, and then a constant force that we can write this way. First, a remark. This constant force, either it is, for example, gravity that you cannot avoid in your problem, or you can apply it by placing the atoms in the inertial frame of a moving lattice. So another way to have that, so an example would be, of course, gravity, or accelerating lattice. So if you use two frequencies different for the standing wave, now let me do it here, otherwise you don't see anything. where the first frequency is swept from the initial frequency to a higher frequency, and the second frequency is swept from a lower, the initial frequency to a lower frequency. If you look at what potential you will get there, you will get a sine square k, and instead of x, k x minus alpha t squared over 2. Because if you look at the electric field with such a frequency, of course, the electric field will be something like e to the I omega 1t, and e to the I omega 1t is e to the I omega t, e to the I k alpha t squared over 2. So hence, as you also have e to the minus a kx, that's why you get an x minus alpha t squared over 2. So everything happens as if now we were in a frame which moves at a speed t squared, and so there is a inertial force which is m x second derivative. Sorry, m is big M. So it's the second derivative of x0 is alpha. Okay, so there's two ways to realize the same thing. Either you really have a constant force, or you take the lattice and you have the little wells which move and accelerate, such that inside the frame which is locked with the wells of the lattice, which moves with the lattice, the atoms feel an inertial force due to the change of frame, which is equal to the acceleration you gave. And so the point is that we will describe the evolution of the system in terms of evolution of the quasi-momentum. A 4, where?
Alpha t squared over 4. Because I think you have to integrate the frequency.
No. This is the frequency I put. I decide to put this frequency. And so this is a frequency which is applied at any time to the laser.
Yes,
So this thing is, you can see in a almost adiabatic way. So the omega is very large as compared to this correction anyway. And so the frequency at any time t is this frequency.
that's true, but the phase is the integral. So in your wave you should have e to the I k alpha t squared over 4.
Okay, I will think about it and come to you later. Okay. Not sure. Let's think of it later, because now I just have 2 minutes. Don't have the time. Just thinking what time I have, in fact. So just to be general for the moment, I will keep some possible time dependence of the force. And what we do is we assume that we start at initial time, our wave function is the block wave function with momentum q0. So again, just to simplify, let me assume that we work in the fundamental band and I drop the n index, okay? So the initial wave function at 0 time is u q of x e to the I q0x. And so what we can do is to make a transform of the Hamiltonian using a unitary transform, which is e to the I over h bar integral on time of f prime. So if the force is constant, it's just f times t. And so instead of looking at the evolution of psi, I look at the evolution of psi tilde, which is u of t dagger psi. And in this case, psi tilde obeys to the Hamiltonian, modified Hamiltonian, which is I h bar d over dt of u dagger times u, and plus the modified Hamiltonian u dagger hu. With this, sorry, there is a x operator missing there. Okay. So the time derivative of u dagger, so u dagger takes a minus sign, such that when I differentiate minus I times I is just 1, h bar goes away. So this guy here gives me a time derivative of this, so f of t times x, and then the phase, which is cancelled by this one, such that this thing here is just f of t times x. And this was the objective of this transformation, to remove the f of t times x term. Okay, so my new Hamiltonian is just the Hamiltonian I have described from the beginning. This one, except that I have to, sorry, I've been too fast. So it removes this term here, but I still have to make the u dagger u operation, and u is a x operator, so it commutes with v of x, but it is this operator is a translation operator in momentum, just as the e to the ip something is a translation operator in space. E to the I something x is a translation operator in momentum. So it translates the p into p minus this stuff. So we have the new Hamiltonian, the transformed Hamiltonian is p minus, so let me call this this thing A, which depends on time if it's like that, plus v of x, but there is no force anymore. And the A is the argument of the exponential. It is a translation of p we make. So the A is minus integral 0 t dt prime f of t prime. Well, there it's 1D, so I don't know why I put some arrows. It's all 1D. Okay. So it's just a number, right? It's a quantity from which it's the momentum from which we translate. So there may be a h bar. No, there is no h bar. No, c'est bon. There is no h bar. Okay. And so now I am left with a Hamiltonian which describes a particle in a lattice in the presence of a gauge field, which is this A. So V commutes with the TA, so we are 1D, so it's TA. And P also, of course, commutes with TA. And in fact, H commutes also with TA at any time. And for this reason, just as before, we have that the quasi-momentum is conserved by H tilde. So the form that psi tilde has, if we start from this form, so psi tilde at 0 time is just also psi, because U at 0 time is just unity. Okay, U of 0 is identity. So psi tilde at 0 time is also psi. It is this guy, and at later time, it keeps the same quasi-momentum. So psi at later time is of the form the same Q and with some dependence, and e to the I qx. So it has still the form of a block function with the same Q. And now if we transform back to psi, we find that psi of x is, so psi of x is u applied to psi tilde, so this one. So this gives u q0 xt, and so this I can also write e to the minus I a x over h bar in short. And so I have to multiply this one by this quantity. So instead of e to the I q0 x, I have to replace q0 by q0 minus a over h bar times x. So in fact, everything is as if I had a new quasi-momentum now. Instead of q0, if I come back to psi, I have a new q which is q0 minus a over h bar. And a is this, so plus 1 over h bar, the integral between 0 and t dt prime f of t prime. So this is the new quasi-momentum of the wave function in the presence of this force. And so if I want to directly link to f, I can write what q dot is. The time derivative of this quasi-momentum is given by, or if you prefer, h bar times the time derivative of the quasi-momentum is equal to the force. So everything happens as if we had some fundamental dynamic relation with the quasi-momentum. The quasi-momentum is modified, is increased by the force. And this is what we will continue this afternoon, and look at experiments and the ways this can be used for, in particular, for metrology. So I just wanted to go to this time, and we'll see to this point, and we'll see the consequence of this equation this afternoon.
So let's say that we have time for only one question.
Well, yes, otherwise, anyway, it's good. It's time for coffee, I think.
Yeah, or just come to
yes.
Hélène if you have a question. Thank you again.